Hello, I am Trevor Dundor, and we'll be examining thrust vectoring nozzles advancement and its impact on vertical takeoff and landing vehicle performance. In order to better understand thrust vectoring nozzles, we will first explain what a thrust vectoring nozzle is. I will then discuss two ways thrust vectoring nozzles are applied, then discuss two different types of thrust vectoring nozzles, and finally present findings on the impact of adding thrust vectoring nozzles on performance. Thrust vectoring is the ability of an aircraft, rocket, or other vehicle to manipulate the direction of the thrust from its engines or motors to control the attitude or angular velocity of the vehicle. We will focus on aircraft specifically. In addition, depicted here is one type of thrust vectoring nozzle. The first source to be looked at is an article on Type A V/STOL propulsion system development. And for those of you who don't know, V/STOL stands for vertical/short takeoff and landing. This is an abbreviation which will be used throughout the presentation. The article discussed a proposal for a mechanically moving vertical/short takeoff and landing vehicle. This vehicle would have a 4 turbofan propulsion system configuration, which uses horizontal nacelles with thrust vectoring nozzles. These thrust vectoring nozzles achieve lift via deflection and distribute the air downwards in order to create vertical lift. The findings of this study reveal that there is a need to evaluate distortion effects on different nozzle positions. In addition, there is a need to determine nacelle/nozzle losses with large-scale hardware to ensure that their findings are accurate. In opposition to source number 1, which looked at mechanically moving propulsion systems, source number 2, a journal article on thrust vectoring in non-moving mechanical propulsion. This article was a review of thrust vectoring in many different configurations of non-moving mechanical propulsion systems. It is a product of a project called ACHION, which stands for Aerial Coanda High Efficiency Orienting Jet Nozzle, which looks to implement a novel scheme to be free of moving parts. And all of these designs are based on the Coanda effect. For those of you who don't know what the Coanda effect is, it is the tendency of a fluid jet to stay attached to a convex surface. In the counterflow arrangement seen in Figure A vacuum is provoked on a slot that is surrounded by a suction collar around the main flow. A stream of reverse flow is created near the wall, and an effect similar to the co-flow system entrains the main flow. Seen in Figure B, we can see a low pressure is generated by means of adherence of a secondary flow to a curved surface, entraining also a deflection of the main flow. These systems are mostly applicable to subsonic conditions since their effect in supersonic flow can become unstable, in particular due to the area rule change. For high Mach numbers, the concepts that became more popular are presented in Figure C and Figure D. The throat shifting control system is based on a converging diverging nozzle. Initially, the shock at the throat is a normal shock, but by applying a fluidic injection before the flow became supersonic. The shape of the post-throat shock is skewed without significant loss of thrust performance. The application of the injection in the subsonic region implies that the losses are minor, thus making the system one of the most promising ones from the point of view of thrust efficiency. Another concept is based on shock vector control. By injecting a secondary control flow into the throat of a diverging section of the nozzle, in this case the formation of the flow is modified by a certain angle, since the secondary injection creates a virtual pressure ramp affecting the main flow. The main flow is deflected due to the orientation of the oblique shock. To obtain maximum deflection, we must ensure that the shock does not impinge on the opposite nozzle wall, since in case the flow impacts on the wall, it will be reflected, thus compromising the system. Another nozzle looked at in the article was the Homer nozzle, which comprises of two main streams that, when in differential mass flow operation, will cause the thrust vectoring of the nozzle. This system can be incorporated in an airplane to achieve V/STOL. Overall, when comparing moving mechanical propulsion systems to non-moving mechanical propulsion systems. The article found that it was demonstrated that classical mechanical moving thrust vector systems imply a reduction in the operative range due to the associated reduction in fuel carrying capability. In addition, the increased mechanical complexity of mechanical moving propulsion systems introduced maintenance issues. Therefore, non-moving mechanical propulsion systems are more ideal if they are able to achieve the same thrust deflection. The next two articles will focus on different nozzle designs for thrust vectoring. This article focused on flow and ventral nozzles for V/STOL aircraft. Many V/STOL designs include a ventral nozzle to provide part of the vertical thrust required. Therefore, this article focused on understanding and predicting the internal aerodynamic flow caused by a single exhaust duct opening. The article presents a numerical simulation of a ventral nozzle and compares the results with experimental data. The experimental and numerical results showed that the flow field within a tailpipe and ventral nozzle configuration is extremely complex. In addition, the results of the study demonstrate that the PARC3D code can predict realistic flow fields and performance for such a configuration, although the numerical solutions are somewhat grid dependent. Overall, the analysis reconfirmed previous experimental results that the flow turning into the ventral duct opening has a limited effect on the upstream flow distortion in the tailpipe. One major way to improve the numerical model used here would be to apply a two-equation turbulence model in place of the algebraic model currently used. The two-equation model would handle multiple walls in a more straightforward manner. This article focused on the design of bypass dual throat nozzle for V/STOL. A nozzle based on bypass dual throat nozzles was designed, numerically simulated, and experimented to achieve V/STOL. This nozzle is called the Nozzles nozzle and can realize flight mode transition by rotating a specially designed crescent-shaped component, which can be seen here in the diagram above and in more detail below. The main results show that the Nozzles nozzle can obtain the ability of V/STOL and supermaneuverability through assistance of fluidic thrust vectoring in only one set of nozzle. This means the crescent-shaped component is the most important component of the Nozzles nozzle. If the outer surface of the crescent-shaped component has no separation, the thrust direction changes by more than 80 degrees. In V/STOL mode, the jet exhausting from the nozzle separates into two channels after the specially designed crescent-shaped component is rotated. One changes the flow deflection angle by the wall of the nozzle and the inner surface of the crescent-shaped component. The other changes the direction under the Coanda effect by the outer surface of the crescent-shaped component, which may cause separation and lead to decrease of the lift. Currently, a gap exists between the currently used three-bearing swivel nozzle's performance and the V/STOL performance of this Nozzles nozzle. The issue lies in flow separation. Therefore, avoiding or controlling the separation and improving the performance will be the main research topic in the future. We will now look at the impact of adding thrust vectoring nozzles on horizontal flight performance. The article focuses on measuring induced aerodynamic effects of the AIDEN nozzle, which stands for Augmented Deflector Exhaust Nozzle. The AIDEN V/STOL exhaust system is a variable area internal-external expansion type non-axis symmetric nozzle with throw area controlled by a variable geometry convergent-divergent upper flap assembly. Plus, it contains a rotating deflector outside the nozzle which can divert the jet downward for vertical takeoff and landing. Overall, the examination found that the AIDEN can conserve fuel through the production of favorable rotation, which dampens perturbations. In addition, a 12% increase in specific range is achieved when AIDEN is vectored at the optimum 7-degree geometric deflection angle when compared to typical flight nozzles. Overall, the effect of V/STOL nozzles go beyond vertical takeoff and landing and assist with horizontal flight as well. Here, listed in order, are the references used for this presentation. All articles come from peer-reviewed journals. Therefore, there may still be some inaccuracies, but at least they have been vetted by experts in the field.